Hi everyone, so today we're going to be doing section 5-6, which is the last section of chapter 5. Woohoo! So we're going to be talking about inverse relations and functions. So if you think about inverse relations, think about inverse operations. What are some of your inverse operations? We have addition, subtraction, those are inverse operations, multiplication, division, right? Exponents versus radicals. We have all these different inverse operations. So now we're going to be talking about inverse relations and functions and how to find those. So let's take a look at example 1. Okay, so it says, what is the inverse of the relation? Remember, a relation is just a set of ordered pairs, right? So here we see what is the inverse? When you think of the word inverse, you think of the word opposite, right? So it is exactly that. Our x values become our y values become our x values. So our independent variable and our dependent variables are reversed. So that's what we call an inverse relation. So to find the inverse, all we have to do is switch our x and y values. Our y's become our x's and our x's become our y's. That represents the inverse relation. It's exactly opposite. Notice we could determine whether the inverse is a function or not based on if one input goes to two different outputs. So notice here we see the number 1 is going to 1 and -2. One input cannot go to two different outputs. So although it is an inverse relation, that relation does not represent a function, right? What it means to be a function is every input has exactly one output. I like to think of the scenario of a letter in a mailbox, right? I could take multiple letters and put it in the same mailbox. Multiple inputs can have the same output. However, I cannot have one letter go into two different mailboxes. One input, for example, the number 1, cannot go into mailbox number 1 and -2. And for that reason, this is not a function. Just because it's not a function does not mean I cannot find the inverse. Let's pause this video and go ahead and try it. Go ahead and switch your x and y values. When you're done, you could check your answer with mine. Oh, what am I doing? So my x values are now 9, 7. Oops. It won't let me. Why isn't it letting me delete? Here we go. Okay, 9, 7, 5, 3, 1, and -1. And our y values are now what were previously our x values, -1, 0, 1, 2, 3, and 4. Is this relation a function? Does every input go to exactly one output? Yes. Therefore, the inverse relation is a function. All right. Now that we're given a function, how can we then find the inverse algebraically? So think about what we just did in that previous example. All we did was switch our x and y values, right? Well, this is really just y equals x squared. So what we're going to do here, first step of finding the inverse of a function, is simply switch x and y. So we're going to switch x and y just like we did when we were looking at the table of values. Why? Because our brains are so used to solving for y. So now how would I solve for y? How would I get y by itself? I would take the square root to both sides. Don't forget, as soon as you take a square root, you need to write down plus or minus. Therefore, we see that y is equal to the square root plus or minus the square root of x. This represents the inverse of x squared. It makes sense that the square root of x is the inverse of x squared because squaring is the inverse operation of square rooting. Now, function notation, we use f to the -1 of x. Just like how we use f of x to represent y equals, right? This just means a function of x, right? F to the -1 of x, this is not an exponent. This is just inverse notation, okay? It's just the way we write that this represents the inverse of f of x. So if I had g of x as my function, g to the negative 1 of x would represent the inverse. It's just saying this is the inverse of g of x. If I had y equals, y to negative 1 would represent the inverse, and so on. So f to negative 1x equals plus or minus the square root x. This is the inverse of the function f of x. All right. How are the graphs of these two functions related? So the function and its inverse, what does that look like graphically? Well, we know y equals x squared is a parabola, right? If I were to graph the square root of x, we would have the first part here, right? We know how to graph a square root function, just half of the graph. But because I have the plus or minus, it creates that second half of the graph as well. How I know that I found the inverse correctly, when I graph the two functions, it looks as though it's reflected over this green line here, y equals x. So if it's reflected over the line y equals x, I know the two functions are indeed inverses of one another. So when you're finding the inverse of a function, you could always check your answer by graphing your original function and the inverse function and seeing, is it indeed a reflection over this line y equals x. Go ahead and pause this video to complete the try it problem. When you're done, you could unpause. All right, so step 1 of finding the inverse. Again, we are going to switch x and y. Everywhere I see a y, I'm going to put an x. Everywhere I see an x, I'm going to put in a y. Now I want to solve for y. How do I get y by itself? Well, I subtract 1. I divide everything by 2. That means y equals 1/2 x minus 1/2. You could also have written it as x minus 1 all over 2, right? That's the same thing. Finally, I'm going to use function notation. F to the negative 1 of x is equal to 1/2 x minus 1/2 to say that this is the inverse function of 2x plus 1. How could we use a graph to determine whether the inverse of f is a function? Explain. We could graph this. No E at the end. What am I doing? Graph the inverse function and see if it passes a vertical line test. Remember, if you draw a line at any point in the graph and it goes through more than one point, then it is not a function, right? Because that would mean one input has more than one output. So you could also graph the original function. If I graph this original function, it's just a line. If I use a horizontal line test, if I draw a horizontal line at any point and it never goes through more than one point, I know then that the inverse will pass the vertical line test, making it a function. Okay, so you could either graph your final answer, see if it passes the vertical line test, or graph the original function and see if it passes the horizontal line test. All right, so we are going to skip example 3 and we are going to move on to example 4. We're going to skip 4A and we're only going to do example 4B. Okay, so let's skip 4A. We're only going to do example 4B. So again, it says find the inverse of the function f of x equals negative cube root of 4x. So again, anytime we're finding the inverse, step 1 is to switch x and y. Step 1 is to switch x and y. So that's what I'm going to do. Now I need to solve for y. To start off, I'm going to divide both sides by negative 1. Now, to get rid of the cube root, I'm going to cube both sides. You agree negative x cubed is just negative x times negative x times negative x, which is just negative x cubed. And finally, I'm going to divide both sides by 4. Now that I've solved for y, this represents the inverse. So using inverse notation, instead of writing y equals, This is the inverse of f of x. And that's it. So basically, switch x and y, solve for y. All right, pause this video and try it for in your student companion. All right, so it says sketch the graph and verify that the inverse will be a function. Write an equation for f to the negative 1 of x. So first of all, let's go ahead and find the inverse here. Notice this represents f of x. Okay, this is f of x. If I draw a horizontal line at any point in the graph, will it pass the horizontal line test? Yes, it will. Therefore, I know that f to the negative 1, the inverse, is a function. Meaning when I find that inverse, it would pass the vertical line test. So why is it a function? Because f of x passes the horizontal line test. Okay, so if I draw a horizontal line, it will never go through more than one point. Now, let's go ahead and find the inverse. I'm going to switch x and y. And I'm going to solve for y. I have to subtract 2 over first. I'm going to divide by negative 1. That's going to give me negative x, right? X divided by negative 1 is negative x. Negative 2 divided by negative 1 is positive 2. Whoops. Now I have to cube both sides. Make sure you use parentheses there. And finally, I subtract 1 over. So therefore, the inverse is the quantity negative x plus 2 cubed minus 1. If I were to graph this, we would see a graph that looks, this is just a sketch, something like this. Notice it passes the vertical line test. Notice it's a reflection over the line y equals x. That's how I know they're inverses of one another. And therefore, it is a function. All right. The last example we're going to be doing today is example 5. We are going to skip example 6 in this section. So looking at example 5, it's saying use a composition to verify inverse functions. What is the inverse of f of x equals 2x plus 5, and how can we verify this? Now, this is the question students always get confused about. Because when they're verifying, they think that they could verify by simply finding the inverse. That is not verifying that two things are inverses. That is finding the inverse. So after we find the inverse, I'm going to talk about, well, how do we verify that they're inverses? So first step to finding inverse, again, we switch x and y, we solve for y. So I'm going to subtract 5, divide by 2. Okay, so this represents the inverse. Okay, so you could have written it as 1/2 x minus 5 over 2 as well, right? That's equivalent. To verify, you want to do two things. We want to show that we're going to use compositions, what we learned in the last section, that f of g of x equals x and g of f of x also equals x. Why would I be left with x? Well, if they're indeed inverses, when we compose the two together, we'll see our inverse operations taking place, canceling out many of our terms, leaving us with just x, okay? So for this purpose, we have f of x equals 2x plus 5, and let's call our inverse g of x. Okay, this is what we got as our inverse, so let's call that g of x. If I want to prove, let's see if I got this answer right, I'm going to find f of g of x and g of f of x and show that I get x as an answer. If I don't, then I did something wrong. So let's see. F of g of x means take take the function f, 2 times something plus 5, and instead of x in f, I'm going to plug in g. So I'm going to put in g wherever I see an x. Well, notice I have a 2 divided by 2 here. These simplify out, leaving me with x minus 5 plus 5. Well, negative 5 plus 5, I'm left with x. It worked. Now I'm going to prove that g of f of x gives us the same thing. So now I take the function g, something minus 5 all over 2. I'm going to take out the x in g, and I'm substituting in f of x, 2x plus 5. Now you can't just go blah, 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 cancel everything out. No, you have to do it algebraically in the correct steps. So what do we see here? Can I simplify these 2's out? No. I see 5 minus 5. That simplifies out first, leaving me with 2x over 2, which is then x. Because I proved that f of g of x equals x and g of f of x also equals x, I can now verify that these two are inverse functions. Okay? So anytime it says verify that two things are inverses of one another, you are not finding the inverse. You are using compositions to prove that the inverse operations are taking place here, and you're left with x. All right. So for part B, are the two functions inverses of each other? So again, if I'm asked, are they inverses of one another? I could find the inverse of f of x and show that I get g of x, right? But anytime we want to prove something, verify, remember your proofs in geometry? Verify. You're going to perform these two simple tasks. Find f of g of x and g of f of x, and you're going to prove that we get x. Maybe we won't get x. Let's see. So here, f of g of x, I have something squared plus 5. Instead of x, I'm going to plug in g. Now, exponents come first, right? So I have to multiply this out first, which means I have to FOIL. I have to write it out twice and FOIL. That's the only way we could square a quantity of two things, right? So, square root of x times square root of x is square root of x squared, or just x. Right? Then here we have negative 5 root x, negative 5 root x again, plus 25. And then I have plus 5. From there, am I left? I could go ahead and simplify this. I'll do it just to x minus 10 root x plus 30. Am I left with x? No. So right off the bat, I'm not left with x. Therefore, no. F of x and g of x are not inverses of one another. Okay? I don't even have to continue doing g of f of x, because if I don't get x for one, I know I'm not going to get x for the other. So therefore, I could know that they're not inverses. Just to prove it to you, I'm going to do this one as well. So I took out the x, and instead I put in x squared plus 5, because that's f of x. Notice here, I can't subtract the 5 because this is inside of the square root and this is not. So therefore, I'm also not left with x here. Alright, go ahead and pause this video and do your last try it problem. Alright, so looking at 5a here, I'm going to do f of g, 5a. I'm going to do f of g of x, g of f of x. This is the only way to verify. Do not find the inverse when it's saying determine, right? We're going to then prove it. So here's how we prove it. The function f is 1/4 times something plus 7. Inside there, I'm going to plug in g of x, 4x minus 7. To simplify, I distribute. 1/4 times 4 is just x, minus 7 over 4 plus 7. Wait a second. This is not going to give me x. So right off the bat, no, they're not inverses of one another. Now I'll try 5b. F of g of x. Even if you do get x for one, still complete the other to show, yes, it works both ways and I do get x. So let's see. We have the cube root of something minus 1 all inside of the cube root. We're going to plug in x cubed plus 1 because that's g of x. What simplifies out first? Well, we see 1 minus 1. So then we're left with the cube root of x cubed. Cube root of x cubed is x. Simplifies out. Now let's go ahead and do g of f of x. Even though we know we're going to get x, let's still just check. Something cubed plus 1. We have the cube root of x minus 1 in for x. Well, a cube root cubed simplifies out as x minus 1 plus 1. Negative 1 plus 1 is also x. So it works. So here they are inverses, whereas in this one they are not inverses. All right, so guys, the main idea here, first of all, let me just say we're going to skip example 6 again. Okay, so that is all the examples we are going to be doing in this section. So now you're just going to practice this section and prepare for the next lesson quiz. Looking at our concept summary here, the main idea, if you're given a relation, set of ordered pairs, we just switch x and y. If you're given a function, you switch x and y, solve for y. We see that graphically, this represents a reflection over the line y equals x. And you do not need to worry about this right-hand side of the concept summary, the bottom right, okay? But these are the three main things here. The last thing you need to remember is composition verifies. So you need to show that the two compositions, this is the same as f of g of x, g of f of x, that you get x each time, okay? So 4 main things here, okay? Don't worry about this small area right here. All right, have a wonderful day.